Okay, hello. This is going to be the first video in this last set of topics that we're going to be studying. So I thought that this was a good time to put a video in because it's some really neat stuff. So I just wanted to talk about it first and just make sure you're clear on some of the notation. It's not hard stuff at all. So first, you've hopefully already read the part about the difference between alpha, beta, and gamma radiation. I think we're mainly just going to do alpha and beta. The AP test doesn't really get into gamma. We'll see. I might look at that too, but we'll see how much time we have. Anyway, I thought that first the book talked about how Rutherford and others had determined the difference between these things and how they penetrated different things to more or less extent, and how gamma rays were the most penetrating, and they went through even fairly thick pieces of lead. It's crazy. So let's think about why they deflect differently in a magnetic field as well. So I thought that just going back and reviewing that would be nice. So why does alpha curl this way if you fire alpha rays out of here? Well, just use your left-hand rule. So you put your pointer finger in. Alpha rays are made of helium nuclei, so that's protons. So it's positive charge, protons and neutrons, right? So protons are positive, so the current would be going like this, and that means your thumb, if you point it, should be pointing this way. So that's why alpha starts to curl this way in that kind of a field. Okay, if you think the same thing about beta rays are basically just electrons. So if you do that, then the current is going like down, and you put your finger in and your thumb points this way. That's why they curl kind of this way in the magnetic field. And gamma rays go pretty much straight through because they're just such high energy. And they're basically photons, so they don't really have a positive or negative charge. They are an EM wave, and they're just such high energy. They're kind of like higher than the X-rays even, which is up there into like the gamma spectrum. That's why they're called gamma rays, right? So gamma rays are highly intrusive, not really affected by EM fields either. So, okay, just thought I'd talk about that for a second. All right, let's look at a couple other things. Okay, so this part is the part that you're actually going to be tested on the AP exam, so I thought we'd look at it closely. It's pretty easy. Alpha decay, we said alpha particles are helium nuclei. That's 2 protons, 2 neutrons. This is the notation, right? That 4 means the total number of nucleons. 2 refers to, that's the atomic number of protons. And if you go 4 minus 2, you get the number of neutrons. So don't be thinking this is like 6 and that there's somehow 6. It's really just 4 nucleons involved in this alpha particle that's being emitted from, in this case, radon. Radon is one of the most common substances to emit alpha particles. That's the thing that Marie and Pierre Curie, that's one of their most famous substances that they worked with. So in this case, we have radon, radium. I'm saying it wrong. Radium, and it's decaying to radon plus a helium nucleus. So the parent in this case is radium, and the daughter is radon. So they're pretty close to each other. If you look at the periodic table, they're going to be right next to each other over on that right-hand side. So you're definitely going to want to be looking at the periodic table quite a bit. Anyway, they have this notation that says like N and N prime. Anytime you have prime in physics or calculus, it means something new. In physics, this gives like the parent to the daughter, or the old to the new, however you want to say that. Don't get confused by the notation. And once again, when this decay happens, the reason it goes from 226 to 222 in terms of the atomic mass number is because the thing that's emitted is that helium, and it's got 4, right? You don't want to think of adding 4 plus 2. Remember, the 2 represents the protons, the 4 represents the overall nucleons, or protons plus neutrons. It's not 6. So I just wanted to make sure we're good on that. The next page, the top of it, where it talks about disintegration energy. I don't know if it's such a big deal, but the main part of that you should take away, I don't like some of their notation. It's just too crazy. It has relativity in there. We're going to do E equals mc squared here in a bit, in this last chapter, or last group of chapters, but I wouldn't look at that too much. The main idea with disintegration energy is that when these alpha particles are emitted, you have 2 types of energy that come out. and of course the overall energy is conserved. You've got the kinetic energy of the alpha particle, and then you can kind of think of it if you have like a particle of, in this case, what are we doing in this example? Uranium. So what is that? Just U. And uranium emits an alpha particle, which is just a little helium nucleus, basically a helium nucleus. And when it does emit that alpha particle, it transforms and becomes something else, in this case thorium, which is less by 2 neutrons and 2 protons. That's why it goes from 232 to 228. But the idea here is that when that happens, this guy, we're going to see, acquires really a lot, an enormous amount of kinetic energy. So he has some of the kinetic energy, we'll call it kinetic energy 1, and this guy, of course, like recoils when you fire this. Think of the uranium atom as like a gun. He's going to probably, so there's a lot of kinetic energy going this way from the alpha particle, but he's going to recoil a little bit too. So you have like another kinetic energy. So you have those two kinetic energies, and we'll look at that in the second example here in just a sec. So in this one, I think it just says to calculate the disintegration energy, which is those two things combined, the total. So what we do is we say, okay, uranium, how much is that? And we say, all right, so uranium, if you look it up in the back of the book, let me just confirm that this number is uranium as it appears in the periodic table. Let's see, where is uranium? 230. Well, this looks like it's a different isotope of uranium, so that one is not actually what's in the back of the book. So, whoops, my bad. This is uranium-232. In the back of the book, the only one that's in the table is uranium-238. So, this one has a slightly different number of neutrons, right? Anyway, so they're saying it starts out as this much. So that's how many atomic mass units it has. And what we're going to do is we're going to subtract this guy. So notice this is only different, I think, right there at that decimal place. So why are we subtracting that guy? So I think that the reason we're subtracting that guy is, let's think about this. So the daughter, we're thinking about this reaction over here. So I need to draw a new picture. So let me think of drawing it like this. You've got uranium, and then after the reaction, after it emits that alpha particle, it becomes thorium plus some little helium nucleus. Okay? So what we're doing first is looking at the products and saying, well, this guy was that 228. That's how much his mass is now. Then we've got the helium little guy, and that's this 4 number. So if we add those up, we get the total amount of mass in the product after that alpha decay has occurred. So if we compare that to the mass in the original, which is this, we notice that it's a little bit less, isn't it? You can see that it's a little bit less. Like I said, these decimal points are the same up until this amount. That guy is less than this that we started off with. So the question is, why is it less? Well, I think this is an example of E equals mc squared, where mass becomes energy. So we're going to work with E equals mc squared in a second, but that's basically what just happened here. This tiny little amount of mass became energy. So how much mass was it that was lost? So we subtract and we say the mass that was lost in this transformation, in this decay, was that much, not very much, and then we can convert that using the conversion for atomic mass units and mega electron volts. Remember, this capital M means electron volts times 10 to the 6th power. That's what mega means. But anyway, we get that many electron volts was how much disintegration energy there was. Now, like I said before, how much of that is the kinetic energy acquired by this guy as he squiggles away, and how much of it is like the recoil energy of basically acting on this thorium atom. So that's what we're going to do in the last example in this video, is look at that. So we have like the alpha particle, looks like they did it the other way. It's being shot this way, and the daughter nucleus recoil going the other way. So in this kind of a situation, you're going to have conservation of momentum. So you can see that their subscripts here. I think I'm going to zoom in. Let me see if I can zoom in on this. I can't see too well. Do I have a zoom here? Oh, I don't know if I do. Let's see. Ah, there we go. That's kind of better. So you can see the subscripts here. The alpha is obviously the mass and velocity or momentum of the alpha particle, and the d means daughter. So don't get all confused by the subscripts. It's not really that big of a deal. Okay, so first what they did here is they said, okay, conservation of momentum, you get this. So then you solve for the velocity of the alpha particle. What they're asking us to do here is say how much of that disintegration energy that we just got, this is the same from the previous problem, right? Is the alpha particle have, and how much is the recoil for the daughter nucleus. Okay, so we say, okay, we've solved for the velocity, so the kinetic energy, or the part of the energy acquired by the alpha particle, is going to be 1/2 mv squared, with that v going right here. So then we say, okay, let's see, what else can we do? Well, we know that that v is this, so we can plug that in and square that. And then we can say, okay, what happens if we actually do that? So this becomes squared in that. So you get one of these left on the bottom. And md squared. Looks like they rearranged it and kept one there and one there. Velocity d squared's right here. The reason they rearranged that, let me zoom back out here. The reason they rearranged that is because if you look at this part, isn't that another kinetic energy expression? In fact, this is the kinetic energy of the daughter nucleus as it recoils. So I think that that's what they did here, said that that red part is the kinetic energy of the daughter nucleus, and this is just a ratio of masses, which we know, right? The mass of the daughter was that mass of thorium. I think that's what this came from, right? The daughter was thorium. This is like a thorium particle, like in our previous thing, and this was like the helium alpha particle, right? And mass of the alpha particle is the mass of the helium, so that's easy. So we reduce that, and we get 57 kinetic energy of the daughter. So in other words, this says, let's be real clear about what this says. It says the kinetic energy of the alpha particle is 57 times the kinetic energy of the daughter particle. So then what they're doing is just, thinking about that. So the total disintegration energy, which they call Q, whatever they called it, who cares, is the alpha particle plus the daughter particle energy. So we get the alpha particle is 57 of these, and then one of those. There's 58 of those total. So obviously the kinetic energy of the alpha particle is 57 out of 58 of the whole. Q is the whole, right? This is like the total. So then we can multiply what we had up here in the previous example for the total energy and take 57/58 of it, and we get that pretty much all of it is the alpha particles. The alpha particle is really what's moving here, right? Its velocity is a lot greater, and it's basically got most of that energy caused by this interaction. Okay, hope you found this useful.